why communication networks are so important for us and why quantum communication networks is a part of that in the future. So when we talk about communication networks, and when I've seen people talking in this workshop about communication network, it was either Alice and Bob and more sophisticated things like Alice and Bob and Eve, right? For us, communication networks have multiple communication nodes and edges, and we think about protocols and how to let them communicate with each other. There are things like multiple access schemes, etc. pp. I think in quantum communication networks, it's more link-based communication currently. So when I talk about communication networks, then you see the evolution of communication networks within this slide. From the left, we have so-called cellular circuit switch networks, the PSTNs, public switch telephone networks, the good old telephone as you know it from your grandma. And then we move in the middle where we have the classical internet, and then to something that is now more our networks, how they look like. If you come back to the left on the public switch telephone networks, the interesting part is that it was a highly intelligent network with very dumb end nodes. Right, and that was changed in a really revolutionary design by Paul Barron and others designing the internet, where suddenly the internet, so the network itself, became dumb by design. Right, what they wanted to achieve is resilience in the network. So if you lose certain communication nodes within the network, you can just replace them by other nodes that can help you exploiting things like diversity, multipath, etc. pp. And the intelligent was more and more put to the outside. So if you are familiar with terms like over the top is a cloud server and an app on your mobile device, and the networks becomes the dump pipe in the middle, which was horrifying for network operators. So that is the classical packet switch network. What we are doing now is computing based networks. So we put the intelligence back to the network. We put computing within the network. So still we would have cloud services outside the network, but a lot of the services that we currently have will happen within the network. So over the top is dead, which is good for network operators. And we still would like to continue with this idea of resilient communication, right? So it's somewhere away from some intelligent network, dumb network, intelligent networks. And what we are doing always is we are creating networks that suit our needs. So telephone networks were just wait for connecting places, offering services like voice. So the internet was, if you remember Nokia's slogan, right, connecting people, voice and data for the first time. And now we also would like to embed things into that. So machine type, machine, or machine to humans. Having this in mind, networks, they evolve, that's a normal thing. And currently we have certain trends that we have to follow and to see where the advantages and disadvantages are. If you look a little bit ahead, what are the new things that we would like to embed in our networks? Here's something that me and Holger Boche have discussed a little bit from our vision, especially when you come to this discussion about 6G, right? Maybe some of you have heard it. 5G is a cellular communication system, and it's currently rolled out in the very first form, in a very easy form. And then some people already talk now about 6G without actually knowing what this is. And for us, what was important a little bit is to understand that maybe communications, they will not evolve in the type of frequency usage, etc. pp. Maybe it's more the architecture that we will use in the softwarized world. Now, also the communication between humans and machines, there's something in that, what we are currently doing. And there are other things like identification channels, post-Shannon communication, or, and this is your topic here, more the quantum networks. So let me bring this a little bit into perspective, right? If I talk about human-machine cohabitation, I brought you one example. And again, if you build a communication network, there's always, where's the need? What is it really that you would like to achieve? And one of the use cases is really interacting human and machines. And here in Dresden, we have the excellence cluster for tactile internet with human in the loop. For example, how can you transform skill set that you have as a human towards the machine. Normally, you would like to program it. That takes time, and you need expert for that. But if you take a normal person that is expert in his field, not in programming, in his field, like working with wood, baker man, whatever, why is he not just doing it? And we are just watching every movement, and with machine learning, we automatically create the code, right? So instead of just programming it, you just show it like to a baby. Maybe you repeat it multiple times, and then you do it. That is our initial idea. What you see here is one of our startup Wandelbots. If you have heard my talks about this, was one of the startups we have. And here you see the CEO of Microsoft, who is actually in Seattle training a robot that is here in Dresden. And he's using a tool, the tracepan, for that, showing what he should solder. And over long distances, we would like to make this happen. And it's not only that you stand next to the robot, maybe you can teach a robot in Japan or in the US. The problem there is a little bit, and this is a fundamental thing in communication networks, latency. So when you talk about latency, then you ask yourself, where is this latency produced, right? In the sensor actuator pair, there's always some embedded computing. This has to be mass market thing. So you lose a little bit of time there. Currently, that is one of the major fields where we lose our latency. Then the communication itself, for example, 5G is really tackling low latency communication, even low latency and ultra reliable communication. And then you have one of the biggest problems with the speed of light, which is not fast enough. So currently, the reason why we have computing within the network is that we just place computational power close to sensor and actuator pairs. So now if you want to do something from Seattle to Dresden, you will find out that is way more than 25 kilometers, which would be more or less a distance that we think is reasonable to create end-to-end latency of 1 millisecond, which relates to human behavior in the tactile haptic feedback. So latency is an issue. Speed of light, you cannot improve that. So you have to place either the computing in the right place, or you have to find out some certain tricks to even get something like negative latency, which you can do by prediction of human beings. So things like latency for communication networks is an issue because you cannot improve it later on. You can always improve on bandwidth, on resilience later on by buying more frequency, for example. But latency is often a factor that you design in the beginning and you're stuck with that. There's a nice paper from 1996 about, it's all about latency stupid. A guy from complaining about Apple modem design in software versus hardware. Very interesting paper still. Now, if you then understand now communication, how they evolve, I brought you here the evolution of the cellular networks. We talked about 5G, 6G already a little bit. And here you see the evolution from 1G to 4G network, purely networks without looking into latency, purely in supporting consumer communication. Netflix, web browsing, voice, text messages, social networking, everything in this. 5G is the first one that is talking about communication for things, cyber physical systems, combining control and communication, which is not totally true because the 5G that you currently see, it's called the Release 15, is often a non-standalone network, which means you have 5G antennas connected to a 4G core, which produce the 5G symbol in your device, but not bringing any advantages in latency. Therefore, currently there's another trend. These are the so-called private networks or campus networks. So these are very isolated networks that you can bring to certain fields and overcome locality problems, like in rural areas where you never have the chance to get 5G rolled out so fast, or you're a big company and you would like to keep everything that is communicated on your site secret. And you decide which manufacturer will realize your 5G communication. Currently, there are a lot of projects here with Volkswagen, Porsche, and others. Now, to understand this, I showed you this picture already. There's this campus network, these boxes, they keep everything they need inside. You could not have done this with 4G because 4G was just a link towards the internet, which was the real service. Now the service of a 5G network is the computing power, and the computing power can be moved within the network, and we can move it already beforehand in the box, and everything is there. So service and connectivity comes out of the same box. There's another trend also that they also would like now to go to Open RAN, which is a further step of softwarization of your networks. They're doing this already in the wired domain, so to speak. Even the 5G core is fully softwarized now. The RAN was still a box thing where Ericsson and Nokia can sell you antennas and RAN equipment, while Open RAN means everything in software as well. So highly flexible over there. Now, there's
maybe you can say quickly what RAN means.
Oh, radio access network. There, a 5G network consists out of a core and a radio access network. The core, there's one of them, and RAN, you can have multiple of those. And Open RAN is then a softwareized version of that. There are other trends currently on the Wi-Fi sector. I will not go into detail because it's not touching your area so much. But of course, on the cellular side, we also have some evolution. So 5G release 15, which you have nowadays, then there will be release 16, low latency, release 17, ultra low latency, and so on. There will be an evolution on that. Also interesting is, and this is that, therefore we talked about novel architecture. So campus is a new architecture. The cellular pass here is the same old. But there are even other stuffs like, for example, high altitude platforms. So instead of planning your network and make sure that you have a national-wide network, and campus saying, I just have islands, there's the idea of high altitude platforms, which is not new because we did it 15 years ago in the European Commission already and had research on that. But currently Deutsche Telekom, for example, is putting up airplanes in the air 20 kilometers high and trying to create 5G networks from that. So you may have heard about Google and Loon and all the others that have similar approaches, but this one is interesting because it's stable. So while the others are just floating around or can just have an small area, these airplanes could cover whole Europe. A few of them you need. You will not have so much high data rate. They're flying at 20 kilometers, which is for latency still a good thing, but it's very good for rural areas, for agricultural things and so on. So all of that, if you look at this, some people say there will be a 6G in the cellular evolution plan. I don't believe in that so much because if it's not only a marketing trick, there's no need for another generation, because generation always means every 10 years we are changing our hardware. But as the entrance of 5G is coupled with something like software-defined networks and network function virtualization, everything what you have there is already in software, and that you don't need a breakpoint to say now we have a new generation. Somehow our colleagues, they're having this kind of reflex to say, let's make research on 6G. I like more to say if 6G is future communication networks, and let's think about what it could be. So architectures is something. Cohabitation of humans and machine is something. And there's something I told you before, Post-Shannon. There's the idea how you really convey message. You could follow the standard approach by Shannon, looking at the semantic and syntax, but you can also try to exploit something more than that. We call it Darstellungsinformation, right? Or design information. There's a big work also by Christian Deppe and his colleagues about that. We currently have a project on that. It's a new way of in information theory to convey information. Not going into this so detailed now. More interesting is what can you do with quantum communication, right? If you would have something, a resource like quantum entanglement, right? What can it help there? And without going into detail, I already uploaded the slides. You can have a look at this. We believe that in all of these three paths, like campus, high altitude platforms, or on the cellular part, you could use this. I don't know how you actually create stable enough entanglements in an airplane and let them go upwards, or you do this on the fly and create that. But once you have this source of entanglement, there would be something very interesting. And we are not looking so much into security. I told this yesterday in the panel. We are more interested in exploiting the entanglement more for new type of communication skills, what we are looking at. So, for example, if you come to the old communication networks, in the beginning, we only had end-to-end. End-to-end communication networks, this is the top, what you have there. The problem is their latency, right? Propagation or the distance between sender and relation relates directly into latency. Therefore, introducing computation within the network, softwarization, then you have the possibility to move the computing closer to the actual activity field and reduce the latency by that. Actually, what you do is you just reduce the propagation delay. What you increase is the computing delay. So here you see the new type of network that you can move your service wherever you want in the network, and then you still have some virtualization features there if you want to use them. And then you might get more delay. There's a paper that we wrote on JSEC where we describe what happens if you virtualize. And you see these three curves, the orange, the green, and the purple one. The purple is once you switch on the softwarization, you get an extra penalty in delay. Then with some smart tricks that we are doing, we can improve it a little bit to become the green curve. But we know there's a limit, and this is the orange curve. We are already, this is the result from the JSEC. We are now on halfway on the towards the orange curve. But we know the orange curve, this is the lower bound that we have to respect, and we always have to pay that, right? And here comes entanglement into the picture. Can we do for certain protocols in compressed sensing, in network coding, you name it? Can we maybe do some easy computing on the file layer and exploit the entanglement over there? Together with all the people that here in the workshop, we created this nice book that recently was published by Springer. You can follow our ideas, especially towards this idea, right? Understanding that quantum entanglement can help us for low latency communication. Despite the other things like coding and compression, I yesterday mentioned about the randomness that I like so much, that other people said maybe that's not the right way to go, but I would even exploit that for my certain information theoretical approaches when it comes to randomness, where also Post-Shannon is based on randomness. Another thing, if you, for example, think about airplanes flying in the air, you can maybe use it for synchronization when you have to make them highly synchronous to create cells on a larger dimension. Maybe we can even use that within in the future. Good. This comes back to the very first slide that I showed you. For us, future communication networks following a certain idea where we can serve the people. There's these 4 different fields that we are currently have under investigation, and quantum communication networks is one of them. Okay. For all of that, it's not only the quantum stuff. For the others, we have written also recently some books how to really do the computing within the networks. What is this tactile internet? What can humans and machine interact? What you need for that? So if you're interested, these books are already out now by now. With that, I would like to thank you. I'm actually on the spot with my timing, so at least my timing was perfect. And I hope you understood the rest, and this is what would be also very beneficial for all of us. Thank you very much.